All right, today we're going to go over some logarithm laws, right, which are common tips and tricks that you can do to solve logarithmic equations. All right, so let's start by examining these laws with a couple logarithmic equations, right? Log 3 of 3, right? Well, log 3 of 3, what power do I need to raise 3 to get 3 if I'm growing at a rate of 3, right? Well, 1, right? 3 to the 1 equals 3. What about log 3 of 9, right? If I'm growing at a rate of 3, if I'm tripling, what power do I need to raise 3 to get 9? I need to square it, so that's 2. 3 squared is 9, right? Let's do another one. Log 3 of 27. What power do I need to raise 3 to get 27? 3. 3 cubed is 27, right? Why all these examples? Well, there's something interesting about them, right? If I were to add log 3 of 3 and log base 3 of 9, I would get 3, right? 1 plus 2 is 3. We know that. But that's also equal to log base 3 of 27. That is interesting. That is interesting because log base 3 of 27 is equal to log base 3 of 3 times 9, right? Here and here. So we could formulate this. We could use some variables to say log base a of x plus log base a of y equals log base a of xy, right? If I'm adding together two logarithms, that's the same as having one logarithm, but with these values multiplied. It's very, very interesting. That's very, very interesting. But we notice that this relationship kind of holds true in a different way with exponents, right? It holds true in a different way with exponents, right? When we're multiplying exponents, right, 3 squared times 3 cubed, we add the exponents when we're simplifying, right? So this simplifies out to 3 to the 5. But under our laws, right, we have log a of x plus log a of y equals log a of xy, right? We multiply, which makes sense. Logs are kind of the inverse way of writing exponents. So it makes sense if when we're multiplying exponents, we add powers, that when we're adding exponents, we multiply powers. That says, hey, for anything that I know about exponents, right, I can apply to logarithms. I just have to change them and I have to inverse them, right? I have to inverse them, right? So I'll go with our laws here. Law number 1, we have log a of x plus log a of y equals log a of xy, right? What's number 2? Well, we know that, hey, when we're dividing exponents, we subtract powers, right? That simplifies down to simply 3, right? That says, hey, that means that if I'm subtracting logarithms, that means I divide the powers. I divide the values here, right? So we'd have our second law be log a of x minus log a of y equals log a of x divided by y, right? That's another rule that we can use. For example, we can have let's get rid of that there. We can have log base 2 of 8 minus log base 2 of 4, right? We can do our division here and say, well, that's the same as log base 2 of 8 divided by 4 which is log base 2 of 2, which is 1. Now, just to check our work, we'll do this the old-fashioned way, right? What power do we have to raise log 2 to get 8? 3. What log do we have to raise, power do we have to raise 2 to get 4? We have to square it, right? And sure enough, we do get 1, right? Our answers match. So this tells us that this relationship is valid. It does indeed work. Right, let's do another thing. Let's see what else we can do. What if I add the same logarithm together? Right? What if I have log a of x plus log a of x? Right? Well, I know just because I'm adding to the same thing that I can rewrite that as 2 log a of x. Right? But the adding law, right? The addition law says, hey, if I'm adding two exponents with same base, I can multiply their values together, right? So that means that this is also equal to log base a of x squared. That's interesting. I wonder if it holds true. What if I add 3 of the same kind together, right? Log a of x plus log a of x plus log a of x, right? What am I left with, right? Well, that's 3 of the same thing. So that's 3 log a of x. But we can also write it as this, right? A of x, that's x squared. And then x squared plus log a of x, right? That's x squared times x squared. That's log a x cubed. And we start seeing a pattern in these numbers. And we can generalize it. We can say for any value, right? If we have a number n log a to the x, where all of these are variables, they can be any given number. Well, that's the same as log a x to the n, right? That's the same as that. We have another law to add. N log base a of x equals log base a of x to the n. Let's do an example. Let's see how this works, because that seems a little weird. Let's see what applications it might have. Right? Let's say 4 log base 3 square root of 3. Right? Well, I know that by this rule, right, that's the same thing as taking this 4, right, and raising the square root of 3 to that power. And if I were to rewrite square root of 3 in exponential notation, I'd have 3 to the 1/2, 3 to the 1/2. Oop, that's messy indeed. 3 to the 1/2 raised to the 4th power. I can multiply these together, right? I can multiply them, and I'd be left with log base 3 of 3 squared, or log base 3 of 9, right? How many times do I have to multiply by 3 to get 9? 2 times. My answer is 2. Right, and that's an example of how we can use this power rule, this power law, to move around things and get it so that we can solve difficult problems. Let's put this all together. Let's combine the solve, and let's do a little something to see how this works. Let's say we have log base 2 of 36 minus 2 log base 2 of 3. Right, neither of these are things that we can solve right off the bat, right? Neither of these are, simple powers or squares or cubes of 2, right? So we're going to have to do some manipulation. Right off the top, I can see that this looks a lot like something I can use this for, right? Because that that 2 looks like an n, right? So I'll put it back in. I'll raise 3 to that power. I'll get log 2 to the 36 minus log 2 to the 3 squared, or I can just write 9, right? Now I'm left with log 2 to 30, log base 2, 36 minus log base 2 of 9. Well, that looks like a subtraction problem. So that means I could probably take 36 and divide it by 9 and get it all in one logarithm. So I'll rewrite it this way. Log base 2 of 36 divided by 9. I'll simplify and I get log base 2 of 4. How many times do I have to multiply by 2? Do I have to double to get 4? Well, the answer is 2, right? If I square 2, I get 4. So my answer to this entire problem is 2. And notice I used both multiple laws, right? I apply them in different circumstances to help me get that answer. And that's why these laws are so handy. They let you solve logarithms entirely by hand. No need of a calculator, in ways that you couldn't otherwise be able to do. So when in doubt, just remember these 3 laws, right? Log a of base a of x plus log base a of y is equal to log base a of x times y. Log base a of x minus log base a of y is equal to log base a of x divided by y. And n times log base a of x is equal to log base a of x to the n, right? And notice, one last important clarification, these only work when the base is the same, right? When these are both a, right? If these were different, we could not use this rule. That's important to keep in mind because it can trip you up and you can end up doing the wrong thing if those bases are different, right? So if these bases are different, those rules don't apply. We'll see how to solve problems that have different bases, though, in the next problem. Thank you for watching. I hope you had an amazing time, an amazing day, afternoon, evening, night. So go on and get on with your life and have a fantastic moment afterwards.